Bluetooth for high-fidelity music. But the question is often asked, what quality can we get through Bluetooth? And there are opposing views. The high-end camp says no, while the camp of regular users says it sounds pretty good. Let's figure out what limitations we have and what possibilities we have. And the very first debate we have is whether 16 bits are enough for us, or if we need a 24-bit source to listen at the highest level. And here I found a study for you that was conducted with a fairly large group of participants, and we'll look at the entire demographics and how it was all done. And they had to determine the difference between a 16-bit audio signal and a 24-bit audio signal on very good equipment. And here we see this study, and here you can even choose the language. Let's choose one here. Let's switch to Russian. It's an automatic translator, so if there are any inconsistencies, that's the translator. Originally, this study was provided in English. Well, and the first part is the procedure. And most importantly, let's look at the demographic data. Well, as always, men are interested in audio gear. Women are not very interested. Well, there were a few of them. This is by age. And for me, even for business, this is important. This is the key age group. If I do any marketing, this is my audience. Well, basically, you could say that the main audience interested in music is from 30 to 60. Well, there were different questions. There were musicians and non-musicians. There were fewer musicians and more regular people. Whether you produce music, work in a studio, or are just a regular person, so there were professionals who work in the field. Well, there were different questions about equipment. This is also an interesting question about how much your equipment at home costs. And basically, if I work with this, which is in the 500 to 1,000 range, then a lot of people have equipment that's bigger and more expensive, right? Basically, I'm in the right segment. I can work normally. But also a lot of people have good equipment at home, right? From 1,000 to 3,000, that's already serious equipment. And there, well, quite a lot of people have more expensive ones too. Very expensive ones exist. I was surprised. They're exclusive but were still included in this selection. There are several, but we're focused on the answer here. And then they play different music for them, 24-bit and 16-bit, and watched how this audience responded. If we take an average like that, well, they're very similar, right? There's very little difference across different types of music. And here is a more visual picture, but overall I would say it's 50-50, right? At the same time, blue is the correct answer and red is the incorrect one. Basically, this means that 24-bit didn't always sound better. But I would say that they can't tell the difference if their answers were that close. Even that doesn't matter if they made a mistake and could still tell the difference, but here it's actually the opposite. 16-bit sounds kind of better than 24-bit. So red is the wrong answer and blue is the right one. And if you look, it's 50-50, 50-50, it's 50-50 there. Even the fact that there were more mistakes here just means it's statistics. They can't hear it. People can't hear it. There's different music there of all genres. So the answer is this. On normal, good. On normal, good equipment, we can't hear the difference between 16 bits and 24 bits. And what conclusion can we draw? We can conclude that for, let's say, absolute high-end, the quality of a compact disc is a kind of standard. Yes, it's a benchmark. We basically don't need anything more or beyond that. Probably the industry will keep offering something, but in practice there's no point. There's a link here if you want. You can look it up and check the details yourself. One more concept. We need to talk a bit about theory. Yes, I understand that it's not interesting, but without theory, it's very hard for us to have a conversation. In the comments, it should be mastered on something, yes, and there are theoretical foundations here as well. There is a proven theorem called the Nyquist-Shannon sampling theorem, but in Russia it's known as the Kotelnikov theorem, that a digitized signal can be reproduced 100% if the sampling rate is more than twice the highest frequency of the signal. Well, if in audio our highest frequency is 20 kHz and we use 40 kHz, then we can fully reproduce the signal. But the first standard adopted for CDs was 44.1. Basically, it's derived from the NTSC video signal frequency to avoid mutual intermodulation. It's a complex system. Later, it was simplified to 48 kHz. But in audio, everything stayed the same as before. And also regarding the fact that human hearing perceives mid-frequencies better than lows and highs, you can also do all this quantization in such a way that in the mid-frequencies we do more precise quantization and in the highs and lows, less. This is usually used for compression algorithms. Also in marketing, you will often see a picture like this, which tells you marketing why a 24-bit signal is better than a 16-bit one. But that's not true because we can so a 16-bit signal looks the same when it is fully restored. Basically, there are no differences here. This experiment with people showed that it doesn't work like that at all. But in marketing, they'll show us this picture, we don't know the theory, and we fall into this trap. Basically, this is a lie. This is dishonest marketing. When we lie, that's dishonest marketing. We can talk about the best qualities of something, but here it's not true. You can't do that. So, about why we need 20-bit digitization. These 16 bits fully restore the entire dynamic range that we can hear. But when recording, we need some extra headroom for errors. For example, let's say I'm recording right now. What am I doing? Here, I intentionally lower the recording level because then my room noises will be below the recording threshold. And then, because I digitize my mic signal at 24 bits, I have plenty of headroom and I can bring it back up and not lose anything compared to 16-bit. So that's the dynamic range. This is for errors. How is this also used in sound recording? Well, for example, we have a normal recording and then someone suddenly shouts. Well, emotional people are talking non-stop and then someone in the crowd suddenly shouts loudly. And if we let that shout go beyond the dynamic range, there will be distortions that can't be fixed. But if we set it a bit lower here and someone starts shouting, it will still be captured here, it will still be digitized with full quality, and then we can remove it during audio processing. And of course we'll also put a proper limiter there, and basically all those shouters will be reproduced perfectly. Why do we need 32-bit digitization? When we do very complex digital processing, different effects convert to different standards many times, mathematical errors appear, and that's when we have a backup again. And this 24-bit recording is perfect for us, and when we do the final mixdown for CD, then we convert it to 16-bit, because here our signal has an excess of information and here everything is done correctly. And if we listen to an equally processed signal like this in 16 bits and the same processed signal with the same dynamic range in 24 bits, we won't hear the difference. Two more concepts, PCM and WAV files. Basically, it's the same thing, but WAV files contain service information so that the equipment can determine what it is, how it works, and what it needs to do. So all the information about the uncompressed audio signal in digital form is here, and WAV also wraps it in a kind of shell. It includes the destination and what equipment it's for. Basically, in terms of quality, it's the same thing. Well, here it's explained in detail. You can pause and read it. One more concept. Lossless compression. So lossless audio compression reduces file sizes by 30 to 60%. Well, 60% is almost 3 times, and it doesn't remove any original data, which allows you to fully restore the original audio signal. Unlike lossy formats like MP3 or AAC, it preserves all the audio information. But what do we lose? Yes, we lose time on compression. We have a delay. But we can reproduce the signal itself 100%. Well, there's a format called FLAC, which many people know. Apple has this ALAC. And it's all a struggle for network bandwidth. It's not unlimited. And basically how we decide what level of compression to use is mostly related to the amount of delay we can allow ourselves. So there's one number we need to remember, and that's CD quality at the level of PCM or WAV files has a data rate of 1.4 kilobits per second. That's the standard. You need to remember that, because when we look at different bandwidths, we'll be checking if we can transmit this signal, or maybe another one, or it's compressed, has delays, and so on and so forth. In general, if we look at FLAC, free lossless audio codec, yes, we can compress it down to about 700, but if it's simple music, we can do even more. But how do these lossless compression algorithms work? When we read signals, we read them very quickly. At one point we read it, there's the full amount of information, but after a small fraction of time it changes a little bit. And then we subtract the previous signal from the next one, we get the change, and we transmit and encode only the change. But when we play it back, they know that with each next reading we need to add this difference to the previous one, and we get the full signal. But this digital processing takes a certain amount of time. We put the signal into a buffer, then a pretty powerful processor analyzes it, and with a delay it outputs the compressed signal. This delay is the cost we pay for data transmission. But we don't lose sound quality during playback. Another concept is transcoding. This means converting one standard into another. So the correct terminology in Russian is digital audio transcoding. And then we convert, I don't know, WAV to MP3 FLAC to AAC, or MP3 to AAC. Well, we can do any of them. But here's a very important note. We need to know exactly what that means. When transcoding audio, the source file is usually decoded into an uncompressed intermediate format, PCM, pulse code modulation, and then encoded into the target format. Although PCM itself is a method of encoding raw audio, in the context of transcoding, it serves as an intermediate, uncompressed stage. But what is important here? If we compress to MP3, we lost information, and then we still decompress it into PCM pulse code modulation, but the information is already lost. And when we compress to MP3 a second time, we can convert it to FLAC. Yes, we can, but it will already have losses. Then FLAC will no longer be lossless. And if we convert MP3 to AAC or to the algorithm used in Bluetooth, we get even more significant losses. So if we do transcoding, it will always sound bad. For example, the same MP3, if we compress it from a CD, it sounds about 95% like the CD, but it's very hard to tell the difference. So you can listen to MP3S2 and the losses are relatively small, really small. Well, you really have to listen closely to hear them, but when you re-encode, well, it's a complete mess. And you see how many different format modifications there are. Spotify had this OGGV, right? It sounded fine too, but if you re-encode it, it will be bad. Then there are different standards here that we can switch to: Orbit, Spotify, AAC, and Bluetooth. And as soon as we switch from one format to another, that's it. Bad. So the standard Bluetooth codec, this SBC, it's pretty simple. It has a relatively small delay. And it's widely used. It doesn't require a lot of power. But the quality we can get, for example, from MP3 or CD, SBC can't provide that kind of quality, because MP3 requires a powerful processor. So also regarding lossy codecs, there are different algorithms there, basically. They all use these. But, first of all, there is some data that's below the threshold of hearing. We throw those out, yes. Even if the data is there, we immediately discard it. Second, people have this peculiarity. If there's one loud sound, we can't hear anything next to it. So if we have a strong hit on the xylophone, then any music nearby will be quieter. That hit will mask it, and at different frequencies it happens differently. It's like a mask, and we also discard all the frequencies that are thrown out here. Well, it's the same picture, with a more complex signal, but here, if there's one such bump, we don't hear all of this. Everything gets discarded by algorithms that work with losses. And the data size, for example, of an average song, about 3.5 minutes, is around 80 to 100 megabytes if it's uncompressed. And if we compress it even with MP3 at 320, we can, well, compress it about 10 times. And now we have faster internet, but it mattered a lot back then. Overall, the struggle for this compression continues. Well, that's serious compression, like this file or that one. There's a big difference. Also, how much you can put on a flash drive, right? And how it works, or how these compression spectra look. Well, here it's uncompressed, here it's compressed. So we lose, we compress, and with such rough compression, we don't even produce the high frequencies, above 16 kilohertz. But there's almost no music there, still though. And also some additional data. Well, here is the real spectrum. You can see here it plays very densely up to 20, and here up to 20, well, up to 18. There's a lot that's thrown out. But I can say that first of all, many people can't hear above 12 at all. Try it, only the very young can. And also when we play different musical instruments here, well, the highest note that is written is 4.5 kilohertz. These are all subharmonics of various percussion instruments that get in. This is the upper spectrum. And in general, these losses, for 90% of people, let's say those who can afford to buy expensive equipment, they're already at a certain age, close to 40 years old, and they don't hear this range at all. So we can also listen to compressed audio, and sometimes when we have to choose between convenience and quality, it's quite acceptable. We can definitely listen to it. MP3 from a good source sounds very good. There are many standards. If you're interested, you can read about them yourself. I won't waste time on that. But here's an important table, and basically the algorithms that are used in Bluetooth. Bluetooth won't work without compression. That's a real problem. The bandwidth is narrow, and we have to compress. And here's the standard codec SBC, and it's actually pretty good. If you compress from the original, it's very good. But for example, when we had Spotify compressed at 320 kilohertz, yes, there was a serious loss here. For example, Tidal would sound much better, but now Spotify has caught up. But overall, 97% is the noise range. Even the most dynamic music has a dynamic range up to 70 decibels, and modern music, which is compressed, has much less. In general, all the parameters are off the charts, but it's basically good. And here are others. IPTX, that's the latest algorithm. I can't comment on this one. I don't understand it. It's too big. It should be somewhere... Well, maybe it's an order of magnitude higher than the harmonic. You need to look into it. I think something's wrong here. Yes, if it's so good here and IPTX came later, it's newer. It should be better here. I can't comment on this. I need to take a look. But probably we're interested in IPTX HD. That's the one with high fidelity. And Sony also came up with an algorithm called LDAC. It has two options. There's an option where it works very reliably but with low bandwidth. So there are certain... it works with a compressed signal. And when it operates at home, in a stationary setup with large antennas, then it works at full range. But it's described here, yes, connection quality, best effort. It's like all the others, but if he's at home in a high... Keep in mind that FLAC, if compressed, is 700 kilobits per second data transfer, which means it transmits any CD in full quality. Well, I haven't dealt with this myself. I don't have and haven't had such equipment with FLAC, mostly because of the transfers. You can still find a receiver pretty easily, but for the transmitter you need a special phone or some kind of special device. And even in China you have to search to find them. So I can't say anything about the quality of that. Well, here it's all about the throughput capabilities. And you can see that aptX HD can transmit, roughly speaking, 600 kilobits per second, while LDAC can do 990, well, 1 megabit. You just need to compress it a little bit, and then everything will go lossless. And all the others, they compress a bit more. But the most popular one is like our MP3, but I think it's a simplified version, because it compresses with lower latency, which means it should sound a little worse than MP3. So what do we get? If we take this Bluetooth equipment, we have the latest developments, especially the Chinese have put in a lot of effort. They install the best Bluetooth in digital to analog converters. And here I picked one. Well, look, it has balanced outputs, amazing Bluetooth, and a built-in power supply. Well, it's a cool device, in my opinion. Yeah, the specs are off the charts. The measurements are off the charts. I haven't tried one or heard it, but the reviews are great. Yeah, it's among the very best. Well, look, among the very best today, it's like 120, and here the best is 123. Come on. That's the difference in all its aspects. Will they use the same chips there? If they installed the right power supply, for example, like if the plus and minus 12 volts are also properly set up here, then the output, the stage has a wide dynamic range. It's even hard to beat it. There are no shortcomings. And here they also measured the balanced outputs. Wow, that's amazing, really. There's nothing to complain about. Another thing I liked about this device is that it was designed from the development stage to be inexpensive. There's this one robotic board where everything is in one place. I think it was developed for the European market, because the power supply is built in. Yes, this requires certification, and there are a lot of small details here. I seriously studied a manufacturer called Behringer. They specialize in professional equipment at an affordable price with good quality. You can't beat them in this regard, you just can't. And since many beginner musicians are, well, not exactly wealthy, they can get a full set of the necessary equipment to perform on stage and record. Yes, it's not the best, but we all have to start somewhere, and this is a big niche. Also, pay attention to the details. This volume knob is usually pretty average in this price category. It starts to squeak after about a year, but here they put it on a separate board. You can replace it, or even swap it out for a good reliable Japanese volume knob. There's Alpsip, which is very good. Well then, personally I take my hat off to those engineers who developed this block. And that's exactly how it should be done. If the price is good, that's the right approach, where the quality isn't lost and the price is good. Those who think this way are the ones who win. And here people wrote about him saying how good he is and blah blah blah. Well, for $200 they're eagles. I can't say anything about that. And here we have another budget option, but it's so high up, and we'll go through these budget ones, measure them, see how they perform, because the previous one of course was a really solid one and so on. But sometimes we want to see what these little ones can do, right? So, first of all, there's an original Qualcomm module here, which means everything related to Bluetooth as a technology is done properly here. A separate digital to analog converter, and it's actually pretty good. If you look back, I don't know, 5 or 7 years ago, only the most advanced devices could do what this little chip can do today. And it has a relay that switches between an external signal and a Bluetooth signal. Through a relay, that means no electronic circuits interfere between the external signal and Bluetooth. You need to adjust the levels, but that's a separate issue. There is a voltage regulator on the board. We can set 12 volts, 16 volts there. They even say up to 20 volts, yes. In general, there's a wide range of what and how we can power it. We can also power it from USB. It's a small module, amazing, it has everything. And now let's take a look at different options and make some comments on how they're positioned. This Bluetooth is now used everywhere, even in stationary devices, and we'll also take a look at several measurements from different devices. I won't be measuring that really cool one, I don't have it. I have another one, Fossey, but Audio Science Review has measured it. If we look at the very top one, it's 200 euros, and these at the bottom, I don't know, 15 euros, that's more than 10 times less. And strangely enough, they're pretty close. But that desktop unit, of course, is better in terms of connectivity and everything else. That unit is worth the price too. Well, let's take a look at the actual units. I made some investments here and bought a whole range of these inexpensive units for measurements just to see which models there are. I bought this one to use it as a transmitter. It has the ability to set different standards and choose between them. And its main purpose is to be a transmitter. Well, I bought two of them to see how the transmitter and receiver would work, but its main purpose, this is my key transmitter. Because devices like this have a standard Qualcomm chip, and as a transmitter it will work properly. Let's position these developments. All of these are for headphones. Well, some of them have additional connections, but basically these are for headphones and have a built-in power supply. Well, I have a couple of these. Let's see how they will work. This one is my favorite. I really like this one. It also has a built-in battery. It can work for a long time, and it's specifically designed to turn standard headphones like these into wireless Bluetooth ones. And at the same time, we buy relatively inexpensive headphones, attach a device like this, and it actually works great. It has a large battery and works for a long time. Well, this one is like a tank. It's very solidly built. It can work as a transmitter or a receiver, but it only supports one standard, which is SBC. The smallest one there has the biggest battery. A very good, long-lasting, low-power output amplifier, and it's also great just for listening with headphones, but that one was smaller. And basically the smaller one wins because of its size, but this one's pretty serious. It's a solid little box made of metal. I liked it. There's a small remote and you can turn it on in DSP mode. But this one is my favorite. I actually bought two. One to keep in the box and the other to show off all its features. You see, this digital to analog converter is a good one, the one I was talking about, with all the inputs and outputs. So I bought exactly this model. We'll test it, measure it, and see what it can do. Well, basically that board on the right can do everything, and the one on the left is for headphones. You can also use it for stationary setups. Well, there's also one in a little box here, and actually the one in the box is made really neatly. I tested it and I liked it. Well, here are my headphones. These are pretty good Sennheiser headphones that are specially designed for traveling. They fold into a small shape, making them easy to carry. But I'll be testing all these units with these headphones. They're relatively high impedance, 16 ohms I think, or maybe even 32, I don't quite remember. And we'll first listen to all these little modules and then we'll also measure them. Here I have studio monitors or studio headphones. They have 32 ohms of resistance. Let's listen. Maybe I should also bring out these big headphones. Well, let's measure first. I'll be using a professional signal generator for this. I'll send different test signals to this transmitter and see what we get at the output. I'll also check the entire frequency response, the low end, and so on and so on. Here I have a Qualcomm transmitter. It's a good chip. Yes, it outputs everything very linearly. So if there are any problems, they'll only be on the receiving side. So first I'll measure the transmitter's counterpart and we'll look at the oscilloscope output to see what it shows. That means it's connected. The fact that it's moving, they don't have a common reference signal for synchronization, so they drift relative to each other. That's normal. At 1 kHz, the signal seems basically normal. We see 0.9 at the output. Let's see how it works across the whole range. Well, maybe it drops a little at the high frequencies, but overall it's almost linear. Almost linear, I would say. From the lows, well, at least in the upper register, the lowest ones are hard for us to determine here. We'll look at that separately. But overall, the signal is fine. Yes, it works well at the high frequencies. Let's take a closer look. Now, what about the lows? We go to 400, then 600, somewhere around here it's fine. And if we go up to 1 kHz, it's still the same. 0.9 at the output. But let's go into this lower register. Lower, 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 lower. 600 here. Even lower, 500. But at 300, it starts to drop sharply, somewhere from 500 down. Basically, the signal goes down, and when I listened to it, this module sounded flat. I didn't like it. Actually, it's designed for the Asian market, and those who might be more interested over there in the East don't perceive low frequencies well. The upper register is supposed to dominate, and it's designed for that audience, but for a European listener, it's just not suitable. So, I immediately rejected it. It's excellent as a transmitter, but as a receiver, it's absolutely useless. Now, let's take a look at this one, which is built like a tank. It's not expensive, but in my opinion, it's very well made. Let's check out all the specs of this particular unit. Well, look at this beauty. So, what do we see? We see the same thing moving, and there's a second carrier riding on the carrier. So at the output, there's a Class D amplifier. Yes, at the output, there's a Class D amplifier. The previous one had a Class AB. Well, or even Class A. Here at 1 kHz, there's a clean, nice signal. But if I set, here I'll put a filter. Yes, we clean it up. Well, a beautiful sine wave, 0.68 volts at the output, and let's see relative to this output, without changing the levels, how it will work. Well, here I'm feeding the full spectrum, and it's like a ruler, absolutely clean, plays up to 20 kHz, goes up to 20 kHz by design. Well, let's look at the lower register. Here it's 1 kHz, so 0.69, and let's go down and see how it behaves down there. At 100 Hz it dropped a little. No, actually it even increased a bit. Yes, increased a bit. And at 50 Hz it's the same as at 1 kHz. And what do we have there at 20, at 30? But basically it's a linear signal path. And that's true. When you connect headphones to it, everything sounds perfect. In general, this simple receiver, which only supports the SBC standard, works perfectly. I would say that I'm satisfied with it. It's inexpensive and everything works just right. Excellent. Let's take a look at the one with the external digital to analog converter, which is already, that's a different level. Yeah, that's a different level. It has proper line outputs. Let's check all the parameters, how it works and how it's made. Well, this one. Antenna, all the outputs, lots of connections. It's perfect for various tests and such applications. Well, we've connected it, beautiful sine wave, high output level. I didn't adjust anything at the input, so it's the same transmitter, but the output signal is twice as strong as the previous one. Interesting, interesting. Well, let's apply a sweep from 20 to 20, and you can see there's a slight roll-off somewhere around 18 kHz. But nobody will hear that. The roll-off is minor. Let's look at a square wave at 1 kHz. It's excellent, excellent, very good. Basically, it shows up. Overall, the range is quite linear. There are few spikes, and this is still going through a wireless connection. But it's a complicated process, and still it produces a proper square wave, a genuinely proper one. Let's take a look at the lower register. What do we have there? At 100, at 20, well, it practically doesn't change. At 100, it's the same, just like at 1 kHz. At 50, there's a minimal drop, really minimal. And at 20, Let's look at 25. Well, the very bottom drops just a little, but let's be realistic. Basically, it has a very linear path, a very linear signal path, I would say. A very small drop in the lows. Everything is great there. We can use it as a linear input amplifier, basically. Let's see, this one's in a box and this one's my favorite, because it's fully assembled and costs about the same as that board over there. But everything is done there. You don't need to add anything else. Let's measure what it can actually do. Well, it's connected now, and what I like is that it's made so that I apply 1 volt at the input, and it gives me 1 volt at the output as well. It behaves in general very predictably. And I can use it as a source for a power amplifier or some other device with a linear input. 1.08. So we apply a full sweep from 20 to 20 kilohertz. There's also a slight drop, somewhere around 18 kilohertz. It starts to drop a little, but we won't hear that. There's probably some intention behind it. Overall, very good. Well, let's take a look at the impulses as well. Well, the impulse is excellent. Going through all these circuits, wireless reception and so on, the sine wave, well, it's a very decent unit. And I think it supports all the standards, both aptX and SBC. It doesn't have LDC. Yes, it doesn't have LDC, but still, aptX HD is my target. That's my goal. And basically, look, on the low end, it plays all the way down to 20 Hertz. Well, it drops off just a little. Yes, just a little. Almost perfect. If only every amplifier could work this well. Overall, this one is my favorite. It's the best if you use it for purposes like, well, like a Bluetooth receiver for some device. It plays flat up to 15 kilohertz, absolutely flat, and up to 18 it drops by just 1/10 of a volt. Well, almost no one will hear that difference. It works up to 18 kilohertz without any problems, no problem at all. Well, at 20, yes, it drops off a bit at the very end, just a little, about 20%, yeah. But overall the path is perfect up to 18, absolutely perfect. Who would have thought? Well, let's sum it up. This little winner is for headphones if you modify something into Bluetooth headphones. This Superman, how small he is, how long he plays, how high quality his output amplifier is. I was thrilled about this. Overall, it's a clear winner. If you convert headphones into some kind of, Bluetooth headphones, any headphones into Bluetooth headphones, definitely. It supports all standards, and you can even choose and set them manually. Well, those who developed in this niche, he's such an absolute winner. It's very convenient to use, weighs only a few grams and can just dangle. Well, it's kind of on a wire, everything's perfect. You can also put the wire into a small pocket or something. In general, for me, this is the winner in this category. Among mobile ones, it has a powerful enough battery for long listening, and it supports all the standards, including aptX HD. That's good. That's good. It's a workhorse. Overall, it sounds really good. As a source for the amplifier's line-in, it doesn't really fit, but it has a big battery. If you need something like that, a workhorse to turn your headphones into Bluetooth headphones, it will work because of the big battery. But I like the previous one better because it's lighter, and that determines how you use it. This one will last longer. It's made more reliably. In general, the Chinese are trying to make some equipment and position it. They make a lot of variations, each with some kind of idea behind it. This one is like a tank, but it doesn't have high resolution standards. Basically, this aptX HD sounds better. It sounds better. If the source is good, this one sounds good. If, for example, you listen to, I don't know, speech, news, YouTube, and so on, the bigger one is good. and these two work perfectly as amplifier sources for the line-in. The board is good, but the one in the box I like better. I like that one better. So the winner in this category is the one in the box. But if you want to buy something ready-made, all of these are around 15 to 20 euros, while the one for 200 that I showed, that one is stationary and can do everything. But these sound surprisingly good. I even tried them with such high-quality amplifiers. As I said, the built-in digital to analog converter here plays a role, and it's miniature but good. Well, in general, there is a winner in each category. In this category, the extender for the line-in input, this one, it needs external power. And regarding the headphones, the small one on the left. But to sum up, Bluetooth HD, if the source is lossless, sounds very good. It's hard to tell the difference. Overall, it doesn't interfere with listening to music at all. On large speakers, it sounds good without any noise. And basically, I would say that it fully meets all the needs of just listening to music. The downside is that all of them have a delay, and this delay doesn't allow us to just listen to TV or watch TV and pass the signal through Bluetooth. But I know that in the next development there is Bluetooth with low latency,